Section 4 makes all your wildest dreams come true. There is an easier way to do integration. So the fundamental theorem of calculus, like I said, there's no need to dawdle, is sitting right here. For a function that's continuous over the interval from a to b, we have from a to b, f of x dx, notation that we've seen before, equals, we've been using the limit definition of integration, but now all we need to do is understand what that means right there. What is that? So that's the integral. The integral evaluated at b minus the integral evaluated at a. Okay? So what you're going to do is you're going to integrate this guy here, and then plug in your upper bound into your function that you get, and subtract off the lower bound into the function that you get. And the answer will be the area under the curve, which makes life a lot easier. So the definite integral evaluated from a to b is the integral evaluated at b minus the integral evaluated at a. That's what that notation right there is telling you. There's no need to include a constant of integration with a definite integral, because when you subtract f at b minus f at a, the c would subtract itself out. Because you'd have f of b here with a c in there that you didn't substitute anything in for, minus f of a with a c in there that you didn't substitute anything in for, and then the c minus c would go away. So the constant of integration subtracts itself to 0, disappears. So, 3 examples for you on how to use the fundamental theorem of calculus. Isn't that what that was? Yeah. Okay. So we integrate this guy, and we know how to do that. What do we get? So x to the third over 3, or 1/3 x to the third, minus 3x. And now your notation that you're going to use is this. Technically, you have all of that, and then you're going to draw a bar, and you're going to say evaluated from 1 to 2. Okay, so now you just evaluate. You take your upper bound and substitute it in. So your first, for your upper bound, you'll have 2 to the third, which is 8 over 3, minus 6. Then very important, minus, parentheses again, take your lower bound, substitute it in. That gives you 1/3 minus 3. Then you simplify that down. And this is where like the math becomes kind of, I don't know, tedious, but you still got to do it. So we have 8/3 minus 18/3 for a total of negative 10/3. Then minus, and this is 1/3 minus 3, so that's 1/3 minus 9/3, which is negative 8/3. Okay, I got negative 10/3 minus negative 8/3. Your rules of algebra 1 come into play here. We make that a positive, and we wind up with negative 2/3 is our answer.
So what is the bottom again?
You just get used to it. So let me draw a little fence here. And what are we going to do on this one? This 3 can be written out front. 1 to 4. X to the 1/2 dx. Okay. Now we're going to have this 3 written out front. So we're going to integrate x to the 1/2 when we get, this becomes x to the 3/2, which means that we have 2/3 x to the 3/2. Do I need a plus c here? No, I don't, because it's a definite integral. If it was an indefinite integral with no bounds, then I do, but I don't here. So I'm done. Evaluated from 1 to 4. Okay. The 3 stays out here. Then open up parentheses and evaluate. So we have 2/3 times 4 to the 3/4. No, 4 to the 3/2. I'm going to undo that parentheses there. There's a 1 there. Okay, so we have 2/3 times 4 to the 3/2. Can I put a minus sign here, or do I need to close this and do minus 2/3 again? Okay, so we'll close the parentheses and then minus the 2/3 again times 1 to the 3/2. So I'm just substituting in the 4 for x here and the 1 for x there. We have the 3 times, if it was me, I would factor out this 2/3 so that we can do what Jake suggested over there. And then times, simplify the 4 to the 3/2 minus 1 to the 3/2. Well, that's just 1. You can cube first and then square root, or you can square root first and then cube. Square root first and you get 2, and then cube you get 8. So this is 8 minus, with 1 it's easy, just 1. So this becomes 7. The 3 divided by 3 here is gone, and I have 2 times 7, which is 14. So the last one. Obviously we want to integrate that. How are we going to integrate secant squared? Well, yeah, luckily you have an inside cover of your book.
Oh, look. The integral of secant squared equals tangent plus c.
Okay, so therefore, this integral is just going to be tangent. So we have tangent x evaluated from 0 to pi over 4. So that's going to be tangent pi over 4 minus tangent 0. So the question is, what is the tangent of pi over 4?
Well, the cosine of 4 is
Oh, okay, it's 1. Minus, what's the tangent at 0? 0 over 1, which is 0. So it's 1 minus 0 for an answer of 1. Okay, another example. Find the area of the region bounded by the graph of that, the x-axis, and the lines x equals 0 and x equals 2. So I'm giving you the graph. Obviously, it's a parabola. We're going from x equals 0 here to x equals 2, which is here. And we are finding the area in this region right here. Make sense? Okay. And the x-axis also. So what do we want to do here? Integrate it. So we're going to have the integral from 0 to 2, because that's my lower bound to my upper bound, of 2x squared minus 3x plus 2 dx. Notice how I've written that in parentheses, because I'm saying that I'm integrating this entire thing with respect to x. Yes. So notice that if we were using the limit definition, then we would have to rewrite this as a sum. We'd have to find a delta x. We'd have to find a c sub I.
No bueno.
Lots of work. So let's do it. What do we get? To integrate, you need to increase the exponent by 1 and divide by the new exponent. So this becomes 2/3 x to the third minus, becomes x squared, 3/2 here, plus 2x. All of this Huh?
Evaluated.
Is evaluated from 0 to 2. Okay, so now upper bound first. We have 2/3 times 2 to the third minus 3/2 times 2 squared plus 2 times 2. That's my upper bound minus the lower bound, which is 0 for this guy, 0 for this guy, 0 for this guy. So that makes it really easy. You're going to appreciate lower bounds of 0. So this obviously disappears, and I'm just left evaluating this. 2 to the third is 8, times 2/3 would be 16/3. 4 times negative 3/2 would be negative 12/2 plus 4. Now what? Common denominator? So this is actually 6. We have 16/3 minus 6 plus 4. So yeah, that's really 16/3 minus 2. 10/3 is your answer. So let's just remember the mean value theorem and what it means for derivatives. This is it. What does it mean?
You're just taking an average of the two. That's all you're doing.
5 different answers.
And only mine was wrong.
Yes.
If you have an interval from A to B, then there exists a number or value C that
It was good and memorized up to that point. So this is the tangent line over the interval at some value C. This is the secant line. So if I draw just this and I go from A to B, here's my secant line right here. Somewhere on the interval there's going to be a slope that matches the slope of the secant line. That's what this says. Okay? The mean value theorem for integrations is sort of similar. If the function is continuous on the interval from A to B, then there exists some number C in the interval such that. That's exactly the same wording as the mean value theorem for derivatives. The integral from A to B of the function with respect to x equals f at C times B minus A. That's the mean value theorem for integration. But what does it mean? Well, it means this. C is the average value of the function over the interval from A to B. The average value of the function. To find the average value of the function over an interval, rewriting the mean value theorem is how we're going to need to remember this one. So what I want to talk about first is this up here. What is the meaning of f at C times B minus A? Yeah, so let me draw in a little function here, just made up. And let's go with A here and B here. So B minus A is this distance right here. No. Let's put that C somewhere in here, I don't know where. No, let me move it. Maybe it's over here. So what I'm saying is that there's some value C, so that f at C gives me that. What is that? What is it? What is f at C? A fish. A duck. What is f at C? It's a height times a, so this is a height, times a length, which gives me an area of a rectangle, which is what I just formed right here. So what you're finding in this with the mean value theorem for integration is you're finding the average value here that gives me the average value when I integrate. So the average value of the function over the integral. It's accurate. It's 100% accurate. So you're going to use this form right here to find the average value of a function. And this one comes up all the time. So if it ever says find the average value, or what is the average value, or what is the average speed, or what is the average position, or something like that, you're going to use the mean value theorem for integration. Find the average value of the function over the interval from 1 to 4. Well, because I see average value of, I'm going to use the mean value theorem, which is integral from a to b of f of x dx. Okay, so 1 over 4 minus 1, integral from 1 to 4 of my function, which is dx. That will tell me the average value of the function over that interval. So simplify. We have 1/3 here. I'm going to go ahead and integrate right now. So x cubed minus x squared, evaluated from 1 to 4. So 1/3 is still out front. We have 4 to the third minus 4 squared. Okay, so this is obviously 0 here. So we just need 4 to the third minus 4 squared times 1/3. 4 to the third is 64 minus 16 is 48. So we have 1/3 times 48, which is 16. So the average value of the function over that interval is 16. So let's say this is my function right here. I don't know exactly where 1 and 4 are on here, but I do know that I don't have a y-intercept. Right? Looking at x to the third minus x squared. So like capital F of x equals x to the third minus x squared. That's what I just found. So there's a couple of zeros here. Actually, there's 3 of them. So I'm going to guess that maybe my graph looks something like this. Okay? Find the average value of the function from 1 to 4. Well, where is that exactly? I don't know. But what I do know is that if I graph this guy, 3x squared minus 2x, that graph's going to probably look something like that. And then if I integrate from 1 to 4, so there's 1, there's 4. I can find that area, right? So that area would give me the value of the function, or how much the function has changed from here to here. When I go up here, the actual function, I'll be way up here at 4. Probably. No? Nothing? Okay. Let's graph it then. Graph this function on your calculator. Alright, so this is my graph. We are at 0, 0 here, and I'm going all the way to 5 more windows, so like 4 is somewhere in this area right here. I guess I need to zoom out more, don't I? So to do that, I will window zoom settings and change my Y maximum to something much bigger. There. So I need to find the average value of the function between 1 and 4, somewhere in this region right here. So if I were to find all of these little y values along from here over to here, add them all together, and divide by the number of values that I found, what I'm telling you is I would wind up with 16 as an answer. Okay? So why is that? It's because over here, if you calculate the integral, you find the total area under the curve. But I don't want the total area under the curve. What I really want is that C value that I get. So if I go back here, what I really want is this guy. I want to figure out what that height has to be in order to give me the average value of my function. So somewhere in this region right here is that C value. I don't know, is it over here? Is it over here? I'm not really sure. Somewhere in this region I have that C value that gives me the average, this number right here, which is found by finding this area right here and figuring out exactly where that C value is, maybe it's right there, to form that rectangle instead. So I'm going to chop off all this area here and wind up with just an area of 16, which is what we did. Yeah, so maybe it would have helped if I had said, okay, let's solve this one for f of c. Which means I got to divide both sides by b minus a. And when I do that, I wind up with the 1 over b minus a. So actually, this is like f at c equals 1 over b minus a, which is this right here. This is the form we're going to be using, though. So when we're trying to find the average value of a function, we are finding this value on the function that gives us this rather than the entire area underneath. It's not that I want to know what the integral is. It's that I want to know what the average value of the function is. So let's read the caption in example 5 on page 282 and try to understand the function, the graph, and the solution process. So let's just take a look. That's a cool picture to begin with, but let's take a look at the graph that they give us. We have a bunch of different altitudes and the speed of sound in meters per second on the y-axis. So at an altitude of 10 kilometers, our speed of sound drops from 340 meters per second all the way down to here. And then the speed of sound changes as we change altitude again. So if we wanted to say, well, okay, what is the average speed of sound then? Then we could use this graph and the mean value theorem for integration to find the average speed of sound. Okay? So basically what we'd have to do is, since this is a graph and we don't have an actual function to work with, we'd want to break this graph into a bunch of geometric shapes. Like I see a bunch of, like there, that would form a trapezoid right there. This seems to form a rectangle, another trapezoid, and then some sort of trapezoid there. Or a bunch of rectangles and triangles if you don't want to work with trapezoids. Okay? What you would find then is the area underneath the curve, which is what we're looking for when we're doing the mean value theorem for integration. We need the area under the curve. But then we're going to multiply that times 1 over b minus a to give us the average value. So in this case, your b would be 80 and your a would be, seems to be 0. So it would be 1 over 80 minus 0, which is 1 over 80. Once you calculate all the area here, multiply it by 1 over 80, and you'll have your answer for the average speed of sound. So you can see that they've sort of broken this up, and there's no way we'd be able to come up with 0 to 11.5 and 11.5 to 22. Obviously, they have some sort of data that we don't. We're just looking at a graph up here. Okay? So they know for some reason that this is 11.5. Probably they have the data that generated the graph. So they broke it up into each one of these separate pieces of area, and they wound up with areas that look like that. Then they added all the values together and got the total area under the curve. And then they multiplied it by the 1 over 80, which is not on my screen, but that's what they did to get the average speed of sound.